get to start a new topic today. Curve sketching. Right. So this is, in some ways, the highlight of the course for me, because you do what I think is really cool, which is you take some problem which seems completely intractable. You know, write down some nasty function and graph it, right? And you say, oh, I'm going to reach for my graphing calculator now, or go on the computer and find some Java applet online that will graph for me. But okay, you pretend for a second that you don't have these sort of resources. You want to graph these things. And what you get to do is just a little bit of detective work, right? A little bit of investigatory, I'm not an investigatory journalist, that sort of thing. We're gonna do all sorts of little deductions based on just a little bit of data that we have about functions, and then throw in some calculus to get a little more data. And then we're gonna try to put all this data together to actually graph things. And it's surprising what you can actually do with at least a little bit of precision. So we're going to break this down into a series of steps. So every time you want to graph something, you can go through all these steps to get something nice out. And so the way I remember it is a little story. I say, Dai said, first, critical test. Then a cavity. And then a second test. Okay, so this is how I remember it. It's just a little story. I said, first a critical test, then a cavity, then a second test. Okay, so what we're going to do is go through this and see what all these things are. Okay, so first is D. Okay, and D stands for domain. Okay, we're going to find the domain of a function. I, intercepts. Okay, we're going to look for the x and y intercepts of a function. S, right, coming from sed, stands for symmetry. Okay, so what do I mean by symmetry? Okay, well, we talked a few times already about odd, right, and even functions. Okay, for instance, the sine function is odd, cosine is even. And then you also have periodicity. So for instance, the sine function has a period of 2 pi. Okay, it just repeats itself. Every 2 pi units, it just repeats itself. Okay. Of course, that's really useful if you want to graph something and you know it's periodic, say with period p. Well, then you just need to graph it in some interval of length p, and then you can just copy the graph if you want to go to the left or right. Okay, and so you see these first 3, these have nothing to do with calculus. Okay, these are all things that you've known before you walked into this class, at least in principle. Okay, the next one, well, you probably at least saw this before, but you never really had an effective way of finding it. And so this is, the A stands for asymptotes. So of course, this includes vertical, horizontal, and then there's one more which you may not have seen before. It's sometimes called slant asymptotes. A slant asymptote, well, it doesn't actually even have to be a straight line. So slant is kind of a misnomer, but we'll talk about what that is later. Okay, so asymptotes, we haven't properly defined them. We've talked about them quite a bit. We use the phrase quite a bit, but we'll define this properly. And then comes the calculus, right? The real calculus. So this we're going to use limits to talk about. But where do we get the derivatives? Well, the derivative comes next when we get to ID. Okay, and this ID, in my head, actually becomes I/D. And this stands for the increasing and decreasing. And so, well, we're just going to use the idea that, okay, if a function has a positive derivative somewhere, then the function is increasing. And if it has a negative derivative, then it's decreasing. And we're going to use that to decide where a function is increasing or decreasing. Okay, so that's dissect. Okay, all this makes dissect. And then first, a critical test. Okay, so where is this coming from? So first, a critical test. Okay, well, the first is telling you to take the first derivative. Okay, so this is what's going to be called the first derivative test. All right, or what I called in our second big picture lecture, the F prime test. Okay, but this is the first derivative test. Okay. As a part of that test, okay, you're supposed to find critical numbers, right, which we'll again define, but remember we talked about these are where the derivative was either 0, right, or where the derivative didn't exist. Okay. So this is the first critical. Find first the critical test, right? You take the first derivative test, right? And this helps you find local max points and local min points. Okay. Then cavity. Okay, so cavity comes from concavity. And because I went to the dentist yesterday. Though I didn't have cavities, just so you know, I have perfect teeth, thank you very much. Okay, so this comes from concavity. Okay, so remember we talked about, right, it wasn't just whether a graph was going up, but somehow whether it was going up like a bull or like a rainbow. And then the last bit, then the second test, and these things are related. We might try the second derivative test, all right, or the F double prime test, as I was calling it. Okay. And we can use this to help us find changes in concavity, right? Points of inflection. And we can even say some things about local max and local min. Okay, so Dye said first a critical test, then a cavity, then a second test. Okay, so let's just remember. And what you do is you go through and you're going to collect all this data. Okay, so some of it's going to be very easy to get, some of it's going to require you to take derivatives, right? Some of it's going to require you to take a second derivative, okay, which means take a derivative and take another derivative. Okay? And at the end of the day, you're going to have a lot of information about the function, and you're going to be able to do a pretty good job of graphing it, right? Without a graphing calculator. That's the goal. Okay, so today we're just going to start going through these things. Right, in order, and just recalling what some of these things meant. So first domain. Okay, this should be the easy part. So remember, intuitively, the domain of a function is all of the values of x that you can put into the function without breaking it. Okay. So all of the possible or allowable inputs into a function. Okay, But this definition, well, at least this intuition, isn't very useful. Right? What's useful? Well, what's useful is what is not in the domain. Right? What breaks a function? Okay. So, what are the sort of problems, right, that you get with domains? Well, what's the first problem you're going to get with domain? Zero in the denominator. Okay. Zero in the denominator. Okay. If I put a 0 in the denominator of a fraction, of course it's not defined. And so that function will not have, well, whatever value gives you 0 in the domain. Okay, you have to throw it out. Okay, so that's the first thing you look for. Right? One comment, which is later on when we're going to find asymptotes, we're going to find vertical asymptotes. There's a very good chance when you have a 0 in the denominator problem that you're going to get a vertical asymptote at that point. Right? Why? Well, what happens as the denominator goes to 0, to the fraction? It gets very, very big, right? The limit should go to infinity. Okay. So that's why anytime you see a fraction, right, and you're going to get possibly a 0 in the denominator, you think, okay, 1, there's a domain problem, 2, vertical asymptote in the graph. Okay. This will give you a vertical asymptote. One quick mention, in this particular function, all right, we said it gets really, really big as the denominator gets really, really small. When we say that, we actually mean in absolute value. Because if we put in really, really small negative numbers, we get to be a really, really big negative number. Right? So from one side it goes to positive infinity, one side goes to negative infinity. So we always keep that in mind. Okay. What's another problem we could have with a domain? Square root of a negative number. Right? You have the square root of x, and x is less than 0. What about add 0? What's the square root of 0? 0. Okay, good. Sometimes people worry about that. Can I do the square root of 0? Yes, of course you can. 0 squared is 0. Okay. Now, look at the graph of square root of x. Remember, this is half a parabola tilted on its side. Yeah. Okay. Notice there's a problem at 0. Not even, well, really past 0. Okay, but there's no asymptote. It's not like 1 over x. So just because you have a problem in your domain doesn't mean you're going to get an asymptote. Okay? It just stops. You get to 0 and that's the end of the game. All right? What's another problem you could have with the domain? ln, right? ln of x when x is less than or equal to 0. Okay? So here you really have to throw out 0. Right? Why? Well, what happens to ln of x as you get close to 0? Negative. Yeah, right? Goes to minus infinity, right? You actually have a vertical asymptote there. So what this tells you, so here you get a vertical asymptote. What this tells you is that you don't need to have a fraction with a 0 in the denominator to get a vertical asymptote. There are other ways of getting them. Now, I just want to mention a related problem to this 1 over x, which is when you're dealing with trig functions. Something like tan of x. Right? Remember, you're going to get problems with that. Why? Well, tan of x is sine of x over cosine of x. Okay, so you can possibly get zeros in the denominator. Okay, so let's keep those sort of things in mind. Okay, so these are, mostly, these are sort of the main problems that we're going to run into. You can't put zeros in the denominator, you can't take the square root of a negative number, and you can't take the natural log of a negative number or of 0. No? Okay, so let's just do just a very quick example. What if I have f of x equals 2x squared over the square root of x minus 1? And what will be the domain of f? So what are the problem childs here? Problem children. Yeah, okay, so I have two problems here, right? I have a square root, so I could get negatives, and I have a denominator, so I don't want it to be 0. Okay, so what does the square root tell me? My x has to be greater than or equal to 0, just from the square root. And then, but if it was equal, greater than or equal not to 0, but to 1. If it was equal to 1, then I would get a 0 in the denominator, so I have to throw out 1 as well. Okay? So the domain is going to be all real numbers bigger than 1. Okay, so you can either write that as, well, you can either write it as all real numbers, such that x is greater than 1, or as 1 to infinity, and you use a parenthesis, remember, to denote that you don't include the number 1. Okay. So that's the very first thing. Anytime you're going to graph a function, sit down and figure out what the domain is. Okay? Because for values that aren't in the domain, you don't need to graph anything. Right? There's going to be no values there. Okay, so that's the first part of diced. First a critical test, then a cavity, and then a second test. Okay, so the second one are the intercepts. Okay, and this is just where the graph is either going to hit the x-axis or the y-axis. Intercepts. Okay, so what is the x-intercept? Well, it's where the graph hits the x-axis, right? Okay, so this is easy, right? So we're going to find, when you do intercepts, you're going to find the x-intercept and the y-intercept. Okay, so if it hits the x-intercept is where the graph hits the x-axis. Okay? Now, does it have to just be one spot? No, right? It could go like this. Okay? So maybe it's a bunch of times. Okay, so there it hits 4 times. Okay? So that's a lot. Of course, what are these typically also called? If a function hits the x-axis, right, if it's 0 there, it's either called a 0 of the function or a root of the function. Right? So finding x-intercepts, right, is the same as finding roots, although typically when you use the word roots, you're talking about polynomials. You don't have to be, right? So if you don't like that, you can say zeros. Okay, so the x-intercept are the zeros of the function. How do you find them? Right? So to find x-intercepts, you set f of x equal to 0, okay, and solve for x. Okay. Just like when you have a quadratic, ax squared plus bx plus c. Of course, as soon as you hear that, you might think x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. But when you think that, you're actually answering a question. What are the roots? That is, what happens when I set that equation equal to 0 and solve for x? Okay? What are the x-intercepts of that function, at least of the graph of that function? Okay, so those are the x-intercepts. What about the y-intercept? Well, the y-intercept is where it hits the y-axis, right? Okay, so that's where it hits this field. Okay. How many times can it hit the y-axis? Once. Just once. Why only once? Otherwise, it wouldn't be a function. Yeah? Remember, a function, you can't have two different values for the same x. Right? So you can't hit the y-axis twice, because then you'd have two different values for the same x. Okay? So because it's a function, it can only have one y-intercept. And how do you do it? Well, this is the easy one. To find the y-intercept, compute f of 0. So to find the x-intercepts, you set y equal to 0. To find the y-intercepts, you set x equal to 0. Okay? Okay, so very nice. What would be the x-intercepts of this function? Well, let's see. We have to set this equal to 0, right? So for the x-intercepts, we write 2x squared over the square root of x minus 1, and then we set it equal to 0, and then we solve for x. Okay, now, when you're dealing with fractions, and you're trying to solve for x, right, and the fraction is equal to 0, there's a very handy rule. Right? This fraction is only 0 when what? When the numerator is 0. Okay, it's the only time. So this is going to be the same, right, since there's no x in the denominator, as saying 2x squared equals 0. And of course, from here you should see pretty quickly, right? There's only one value of x that's going to do it. Is when x is equal to 0. So there's only one x-intercept in this case. Okay? And what is the y-intercept? Well, the y-intercept is what happens when you plug in 0 into the function. But we just saw what happens. When you plug 0 into the function, you get out 0. Right? So the y-intercept, right, is y equals 0, right? So you're actually not getting anything new. Right? This x-intercept gave you the point 0, 0. This y-intercept gives you the point 0, 0. Okay, so if this is an x-intercept, right? If you actually hit right at the origin, then that's going to double up. You're going to find that both when you do the x-intercept and the y-intercept. Okay, but of course, if you were doing it over in this case, you would get more x-intercepts than just 0, and you wouldn't get a y-intercept equal to 0. You'd get the y-intercept there. Okay, any questions so far? Tom?
For the x-intercept, since that's 0 and it's out of domain, do we still count it?
Oh, excellent point. Excellent point. Right? The x-intercept is outside of the domain. Yeah? 0, I can't put that in here. We just said, you can't put a 0 into the function. Okay, so this is very good. Okay, so neither of these, well, they're the same thing. This would be the x-intercept if it made sense, but it doesn't even make sense. Right? So this is not on the graph. Okay, so that means, right, is that this gets thrown out. Okay, or this one gets thrown out, and there for the same reason the y-intercept gets thrown out, because it's not even in the domain of the function. Excellent observation. Does everybody see why I had to throw that out? No? Okay. So I'm supposed to have an x-intercept, right? Which x-intercept means it hits the x-axis. And it's supposed to hit it when x is equal to 0. Right? Okay, but I can't put x equal to 0 into this function because it's not in the domain. All right, remember, why not? If I put a 0 into this function, well, sure, the top is 0, but the bottom is 0 minus 1, which is minus 1, and I take the square root, which I'm not allowed to do. Right? So it's not a real intercept because it's not even in the domain of the function. The intercept means I should have a point on the graph, but I can't draw a point there, right? Because the function doesn't make any sense there. Okay, so we have intercepts. Okay. So you can see sometimes you get none. And you have to be careful, right? Because sometimes you get phantom intercepts. They should exist, but they don't. Okay, so what's next? So that's DI we've done now, domain and intercepts, that's DI. Okay, so what did DI say? Well, DI said, SED's the next part. So what does SED start with? Starts with an S. What does S stand for? Symmetry. Okay. So let's just recall again what it means for a function to be odd. So f is odd if, well, if I put in f of minus x. Okay, so for instance, I know what some function is at x. All right, but let's see what happens when I put it in minus x. It's going to be odd if this minus comes out. Now, before we see an example of an actual odd function, right, let's say I know that I have a function whose graph looks like that, at least from 0 to infinity. Right? And let's say I also know that it's an odd function. Well, how can I graph what happens over here? Well, let's see. I know that if I put in, let's say this point here, that's 2, and I get the value 1. Okay, so if I put in a 2, I get a 1. What if I put in a minus 2? Well, this says, since it's an odd function, if I put in minus 2, it's the same as minus f of 2. F of 2 is 1, so minus f of 2 should be minus 1. So I should get a point down here. So what's going to happen? All these things, anything which was up here, right, is going to get flipped down to over here. Everything gets, if you like, you can flip the graph over and then flip it down. Okay, or, well, what's another way of, can you, how do you visualize the symmetry here? What is the graph going to look like? Well, it's got to look something like something like that. So, I mean, for me, the way I see it is I flip it over and then I flip it down. I'm not sure how you guys want to see it. There's a Is it visually clear?
Well, yeah.
Okay. I'm just curious. I'm not sure if you guys can see how it. So, if you know 1/2 of an odd function, you can get the other graph just by flip it across and flip it down. Okay, that's somehow the easiest thing. Okay, so an example of an odd function, and the first one that you always look at is x cubed. You should really start with x, but it's somehow too easy to start with. How do you prove something is odd? Well, all you're ever going to do is just plug negative in. Okay? You plug f of minus x, and then you compute what you get, and you see if it's equal to minus f of x. So f of minus x is minus x cubed. And what is minus x cubed? Minus x cubed. Right? Because it's minus x times minus x times minus x. Right? There's 3 minuses, so it becomes a minus, and then you have x times x times x. That's x cubed, so minus x cubed. But of course, this is exactly minus f of x, right? F of x was x cubed. So minus x cubed is minus f of x. So it's an odd function, and if we graph it, Looks like this. Okay, you get the same thing as if you flipped it across and moved it down. Okay. So it means is all you have to do is graph this side, and then you automatically get this side for free, or vice versa. Okay, so this can be helpful. Okay. What about an even function? Well, f is even if f of minus x. So again, when we're checking odd or even, we'll always put in f of minus x. And it's even if you actually don't change the function at all. Okay, so let's say I have roughly the same picture. Okay, but now I tell you it's not an odd function, it's an even function. Well then, this tells me that if I plug in the negative value of x, I actually should get the same thing as the positive value of x. Which means that I'm just going to reflect this graph across. That's kind of fun. So this is even easier, right? Just reflects one way across. So again, though, it means you only need to know 1/2 of the graph. Okay, so the canonical example of this one is x squared. Right? So if you have f of x equals to x squared, you want to say is it odd or even? Well, you plug in f of minus x, you get minus x squared. And of course this is minus x times minus x. There's two minuses. They cancel. You just get x squared, which is exactly f of x. Okay, so this implies f is even. Okay, and of course this shouldn't shock you when you remember the graph of x squared. It's a nice parabola, right? Which is the same on one side as the other. So you only need to graph half the parabola, you know what the other half looks like. For polynomials, it's very easy to decide whether or not your polynomial is odd or even or neither. Because some things could be neither. All right, let's see, the easy case is, let's say you just have a polynomial of one term. Okay? Well, you look at the degree. If it's an even number, then it's going to be an even function, right? Because when you expand it, all these minuses, well, there's an even number of them, so it goes away. Okay. If you have an odd degree, then you're going to have an odd number of minuses. And, okay, so it's going to be an odd function. All right? What if you combine them? What if you do x cubed plus x squared? Do you think this should be odd or even? Well, don't think. Feel. So we'll enter the dragon reference for you. Okay, well, we just plug it in. Minus x cubed plus minus x squared, which is minus x cubed plus x squared. Okay, it's certainly not the same as the original function, so it's not even. But if you put a minus f of x, then you get minus x cubed minus x squared, which this is not. So this is neither odd nor even. Okay. So not every function is one of these two. Okay, so you have to check. So what's the problem? Well, the problem is you're mixing odd and even degrees. If you have a polynomial which only has even degrees, so x to the fourth plus x squared plus 6. Then you're okay, you have an even function. If you have a polynomial with only odd degrees, x to the fifth minus 3x cubed plus 14x, you'll be okay. You'll have an odd function. Okay? But as soon as you start mixing the terms, you absolutely cannot have an odd or even function. Okay? A couple other examples that are worth remembering are the trig functions. So sine of x. Well, do you remember what the Taylor series was for sine of x? It was, how did it start? So you had to start with its linear approximation. Yeah, so this is the Maclaurin series, right? Starts with an x, because sine of x is roughly x around 0. Starts with x, and then what's the next term? What happened? Remember what happened with those, the degrees in this Maclaurin series expansion? What was e to the x? I started with 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial and so forth. And you remember how e to the x was somehow a combination of sine of x and cosine of x. Okay? And so the sine gives you the x, and what was the next one? X cubed over 3 factorial plus, and then it alternates. And so you only get every other term, right, of e to the x plus you get these alternating sign business. Okay? But you're getting the odd degreed terms. Okay, and so immediately, right, we can see that sine of x is an odd function. No offense. Okay, and what about cosine of x? Well, cosine of x, that has the missing terms from e to the x. Right? What are the missing terms? 1 minus plus x to the fourth, the 4 factorial, right, minus plus. I said it already, but let's recall. When you have a constant, just to say you have a constant, is that an odd function or an even function? Or neither? Well, let's check. F of x equals c. There's a constant. What's f of minus x? Not minus c? No, of course not, right? It's a constant function. It doesn't matter what you put in for x. You get c, right? Okay, so f of minus x equals f of x. Okay, fine. So it's an even function. Good. So you have a whole bunch of even functions. You add them up. Get an even function. So cosine of x is even. Okay. So this is not so bad. Now, I guess I could write a full sentence. Is an even function. Now we saw over here, if you add together an odd and even function, you just screw the whole thing up. Okay? But what if you multiply? What if I have, say, f is an even function, and g is an odd function? By the way, the fn is for function, not fn. Fn, good notation. Okay. Okay, so let's say I have these two functions and I multiply them. F times g. Okay, which remember what that means. If I multiply two functions together, f times g, it just means I plug in x for both of them and then multiply. Okay, it's just the most natural meaning we can think of in our algebra of functions. Okay, so what if I put in minus x? So f dot g of minus x. Well, this is f of minus x times g of minus x. Now f was an even function, which means f of minus x equals f of x. And g of minus x equals minus g of x, right? I'll move the minus to the front. But of course, this minus f of x g of x is the negative of this. And so this is negative f dot g of x. So what kind of function is f dot g? It's an odd function. Okay, so if I do an odd and an even, I get an odd. All right, let's make a little table and see if we can't do this more generally. Okay, so if I have an odd, an even, and an odd, and an even, okay, so I'm going to multiply. And mind you, remember multiply is going to really work as well as divide, but we'll talk about that in a second. So we just said if you have an odd times an even, you get an odd. All right, well, actually, strictly speaking, we said if you do an even times an odd. But of course, multiplication is commutative, right? So either way, it's okay. So an odd times an even is an odd, or an even times an odd is an odd. Okay, so then the only things we have to worry about is odd times an odd or an even times an even. Okay, so what's going to be an odd times an odd? Right, it's going to be an even. Why? Well, if you have f and g both odd, then right, f times g of minus x is going to be f of minus x, g of minus x, which is going to be minus f of x times minus g of x. The minuses are going to cancel, so you get f of x, g of x, which is f dot g of x. Okay, so you get back what you started with. Okay, so that's an even. Okay, and what about even and even?
Even.
Okay, I've heard even and I've heard odd. That pretty much covers it, doesn't it? Let's check it. Okay, so f and g are even. F dot g of minus x is, well, it's f of minus x times g of minus x. But f and g are both even, so f of minus x is f of x. G of minus x is g of x. And this, by definition, is f dot g of x. So you get back what you started with again. So this is equal. Just a note. Let's forget about functions for a second. Let's talk about numbers. Okay, just natural numbers. Okay, those also can be odd or even. Let's say I add them together. What happens if I add two odd numbers? Even, right? 3 and 5 is 8. Right? 2n plus 1 plus 2n plus 1 is 2 times n plus m plus 2. Right? So this is even. Okay, what about an even plus an even? Even, right? 10 plus 12, 22, nice even number. And what if I add an odd and an even number? Odd. It's always odd. It's the same table. Okay, so odd and even functions, when you multiply them, if you want to tell whether it's odd or even, it mimics exactly just what happens when you add two numbers. Okay, and now the last thing which is going to make all of this worthwhile is division. What happens, so say I have f is an odd function. And I look at 1 over f. Okay, this is a new function. All right, let me call it g. Okay, so g of x equals 1 over f of x. Of course, we have to make the no, we're not allowed to do that when f of x equals 0. Right? So g of x is only defined when f of x is non-zero. Okay, fine, we got that out of the way. we can still ask, what is g of minus x? Well, it's 1 over f of minus x. But f was odd. So this is 1 over minus f of x. And I can pull this minus to the front. No? So this is minus 1 over f of x, which is minus g of x. So if f is odd, then 1 over f is odd. What if it was even? Well, minus x in here can become minus x there, and then it's just going to go away, right? Because it's an even function. And so you're just going to get back g of x. Okay? So if f is even, this implies 1 over f. Oops. Is even. Okay, so how can we combine now division and multiplication to say something general? Okay, well, let's say I have f is an odd function and g is an even function. And I want to know what is f divided by g. Well, so an odd divided by an even. Well, instead of thinking about it that way, I could say this is f times 1 over g. And now, instead of thinking, oh, I have an odd divided by an even, I have an odd times an even. Right? Because we knew if g was even, then 1 over g is even. So I have an odd times an even, and now I can go to my table, and I think, odd and even is odd. So this is going to be odd. So an odd divided by an even is odd. So it actually is going to satisfy exactly the same rules as the multiplication table. So whether it was times or it was divide, right? It's going to satisfy these rules. Odd times an odd is an even. Odd divided by an odd is an even. Okay? Just because of this argument. Okay, so this is going to be very useful because let's say I write down some complicated formula that can be broken down into odds and evens. For instance, f of x equals, say, sine of x times x cubed minus x over 2x squared minus 1 times cosine of x. Right? If we want to know if this has symmetry, so if it's an odd or an even function, well, I just do it piece by piece. I say, okay, sine of x is odd, right? I can make a little table, right? So let me use well, that's good. How about a 0 for even and a 1 for odd? Okay, so yeah, sine was odd. So it gets a 1, okay? And then this is a cube and a 1, so this is again an odd function. Okay? So I write everything in terms of plus, and then I use this arithmetic. Okay, then down here I have a square and a 0th power, so that's an even, so I get a 0. And it's times cosine, which is even, so this is plus 0. Okay, so I get a 1 plus a 1. Okay, so it's an even plus an even. I'm sorry, I have an odd plus an odd, that's going to be an even.
Wait, what is the 1 again?
So 1 and odd, sorry, I'm going to say 0 is even and 1 is odd. Okay, so I have an odd plus an odd, which gives me an even, and I have an even plus an even, which gives me an even. Okay, now don't read this as 0 divided by 0. Okay, read this as even divided by even. Right? And we just said even divided by even, the same as even times even, right? Which is even. Okay, so it looks really bad up there. Looks like I've said something really stupid. Okay. But this thing now is an even function. Okay? And imagine what you would have to do to show this directly. What would you have to, you'd actually have to plug in minus x, which means you have to plug in all these minuses everywhere. I mean, that would be a real pain. Okay? So this says as long as you're just multiplying things, you can just plug things in directly, piece by piece, and look at things component-wise. All right? As soon as you throw pluses in, now you're in trouble. Right? Now you're in trouble. Unless everything is of the same type. Right. For instance, I can now throw on an even function here. That would be no problem. If I added plus, how about plus secant of x? Why is secant even? 1 over cosine. Cosine was even, right? We just saw even function, then 1 over it is even. Okay, so now I have an even function plus an even function. Okay, I'm not doing any damage there. I can add like symmetries and I stay the same. If I add unlike symmetries, unlike, they don't like each other. If they don't like each other, they're not going to add well together. But if you multiply them, you throw them together, then they're going to mix. Okay, so then this whole thing, so that's also even. Right? And then the whole thing will be even. Okay, but if I throw in cosecant, which is 1 over sine, and so it's odd, I get no symmetry. It's nasty. Okay. So any question about odd or even functions? Okay, let me just finish up symmetry by reminding you about periods. Okay. So formally, you say that a function f is periodic with period p if f of x plus p equals f of x for all x. Okay, it just says that if you know where the graph is now, then you're also going to know where it is p units later. Because it's just going to repeat. And of course, the example that you all know is the function sine of x, which has period. All right, what's the period of sine? 2 pi. All right, the period is a number, okay, and it's 2 pi. Okay. And if you graph sine of x, you know that you can start here down at 0, and you go up, and you go down, and you go up, and when you get here at 2 pi, you now know that everything about the graph is hidden already between 0 and 2 pi, right? Because when you go to the right or to the left, it just repeats itself. F of 0 is the same as f of 2 pi. This right over here, what number is that?
Pi.
Pi. F of pi is the same as, well, f of minus pi. Right? Sine of minus pi equals sine of minus pi plus 2 pi equals sine of pi. Note, though, that sine of 0, right, also equals sine of pi. So you might think, well, wait, why isn't the period pi then? Because I mean, here, okay, I mean, here you go all the way to 2 pi and you get the same thing. But why isn't it? I mean, if sine of 0 plus pi equals sine of pi, why isn't the period pi? What's that? I mean, you can see on the graph, right? Around 0 and around pi, there's certainly a difference. Right? At 0, it's going up. At pi, it's going down. Okay? So intuitively, yeah, it's not the same part of the graph. But with this definition here, Right? Isn't this all I'm requiring? That f of x plus b equals f of x? I mean, shouldn't that tell me that the period is pi? What's the key? Well, the key is the very last bit for all x. Okay? It works at 0. But what if we went up here to pi over 2? Right? Sine of pi over 2 is 1. What is sine of pi over 2 plus pi? Negative 1. Right? That's 3 pi over 2. So that's why pi isn't the period, right? It may work. You may have a relation like this for one particular x, but the period rule says it has to work for every single x. Okay? And that's why you need 2 pi. Okay, just an observation. What's the period of cosine? It's also 2 pi. Okay. So it will probably be worth your while to go look up, in any of your old pre-calc notes, or go anywhere online and look at all the different trig functions, okay, and see what their periods are. Okay, just look those up. Yeah?
Is that an even or odd function?
This one?
Yeah.
Well, this part is even, and this part is even, so you add them up, it's still even.
I think it's odd because when you multiply even and odd, multiply and odd.
What did you say? Well, okay, let's see. Up here, this was odd, and this was odd. So you multiply 2 odds and you get an even. And then you divide, down here that's even and even, so they get an even. So you have even divided by even, so it's still even. And then we add an even, and it's still even. Yeah, actually, a different way to count, instead of using 1s and 0s, use 1s and minus 1s and multiply. Right? It's just, forget about the secant business. Go back up here for a second. Instead of using, let's use 1 for even and minus 1 for odd. Okay. So now you get minus 1 times minus 1, because they're both odd, over 1 times 1. Right? Because they're both even. And now on top you get 1, and on the bottom you get 1, and 1 divided by 1 is 1. So a different table that you could draw out for this, right, is the table 1, minus 1 and 1, right, for multiplication, right? And as you get 1, minus 1, minus 1, 1. Okay, and if you identify 1 with even and minus 1 with odd, then you see you get the same table. Okay? It's a nice group of order, too. Okay, any questions about odd or even or period? Typically, with period, you should be looking for things like trig functions. You take a polynomial, right? These are not periodic. Logarithms, not periodic. Exponential functions, not periodic. Okay. It's usually trig functions that are going to be periodic, so that's what you're looking for. Okay, let's see. We have until, is 15 after?
Yep.
Okay, well, let's see how far we got. We did domain, right? We did intercepts, and we did symmetry. Okay, so let's just very quickly start on asymptotes, and then we'll do more tomorrow. All right, so like I said, there's going to be 3 kinds of asymptotes: horizontal, vertical, and slant. Okay, but we're going to be mostly concerned with horizontal and vertical. So let's start with horizontal. So here's how I'm going to write it. function has a left horizontal asymptote. Now, this left business, this is not a standard bit of terminology. I'm just doing it because I want to emphasize that a function can actually have two horizontal asymptotes. Okay? So a function has a left horizontal asymptote if there exists a real number, which let me call it L. So there exists a real number L such that the limit as x goes to minus infinity of f of x equals L. Okay, so the left horizontal asymptote is an asymptote happening on the left side of the graph, right, over on the negative infinity. And then I'm going to be able to say the exact same definition for a right asymptote. So a function has a right horizontal asymptote if it's the same thing, except now I'm doing it on the right side, so the limit will be to positive infinity. Well, I need this expression here too. So if there exists a real number L such that the limit as x goes to infinity of f of x equals L. Okay, so this tells you what they are formally. What does it mean pictorially? Okay. Well, let's assume that I have some function f of x such that the limit as x goes to minus infinity of f of x is 2. Okay, so I can compute this limit. So I sit down, I compute the limit, I get 2, and then I say, okay, fine, that means as I go to minus infinity, this function is approaching this value 2, right? The line y equals 2. Okay. Now, what does that mean as far as what the graph looks like? That's hard to say without more information. It could mean that it's going like this. It could be going like this. Getting close to 2. It could be going like this. There's a common misconception about asymptotes that a function can't cross an asymptote. That's not true. It can cross an asymptote. Right? The way I've defined it, the function could be the asymptote. Right? Think of a constant function. F of x equals 2. What's the limit as x goes to minus infinity of f of x? 2. Right? So by my definition, it has a left horizontal asymptote. Right? In fact, that asymptote is a function. It's hitting it every point. Okay? And here this one. Okay? It's crossing the asymptote infinitely many times. It keeps going back and forth, but kind of the amplitude of these little curves is getting smaller. Okay? And getting very, very close to 2. Okay, as you go to minus infinity. Okay? An asymptote doesn't mean that it can't be touched. Right? It just means that the function is getting very, very close to it. Okay? Possibly touching it. Okay? So if you want to find the horizontal asymptotes for a function, all you need to do is sit down and compute the limit as x goes to minus infinity, and then the limit as x goes to positive infinity. Let's say this one is 1. Okay, well, as it goes to positive infinity, if it's a value 1, that means you have a right horizontal asymptote. Right? And the same thing's going on, right? It could be going down like this. It could be coming up like that. Right? It could be crossing over many times. Okay? It could be crossing once. Right? Another way you could have hit this too is you could have gone down once and then come up. So a useful thing to check is if a function crosses an asymptote. In the same way that we check whether or not a function crossed 0. Instead of taking your function and setting it equal to 0 and solving for x, you can set it equal to the asymptote and let it solve, and then solve for x. Okay. Sometimes this is prohibitively difficult. Right? Usually when you solve for 0, somehow it's easier to solve for the thing. You know, if you have a quadratic and I solve it for 0, okay, I just have the quadratic formula. Okay? If I have it solved for a number, well, now I have to work a little harder. Right? And if it's not a quadratic, if it's something really, really bad, something ugly with lots of garbage in it, you know, it might not be that hard to figure out where this thing equals 0. In fact, you can tell pretty quickly, if x equals 0, you should get 0. Yeah? But if I say, where does it equal 7? Well, now it's trickier, maybe. Okay. So next time we'll start up. We'll figure out what a vertical asymptote is. Okay. And we'll review this a little bit. So you can see we're almost into the calculus part. So this is the basic stuff.